All right, welcome back again. Today we're going to be talking about section 12.3, which is all about the dot product. This one's a really interesting one because we've been talking about vectors, and now we're going to talk about a new way to operate on vectors. So this may not be something you've thought about in the past, but we're going to start everything with a motivating question. So let me get started. All right, so this is section 12.3, and here's the overview. We're going to start with a motivating question, and then we're going to actually get what the dot product is. We'll talk about properties of this new operation. We'll get a geometric interpretation of this new operation. We'll build some intuition for what this new operator is giving us. Then we're going to define orthogonality. This is one of the nice things about the dot product or just an inner product in general, is it lets you define a notion of perpendicularity that is generalizable. Always want to have an eye toward generalization. Then we'll talk about direction angles and direction cosines, vector and scalar projections, a physics application for work. I mean, the physics application of work, and then helpful technology, once again, Mathematica. All right, so here's the motivating question. How can we possibly multiply two vectors in a meaningful way? So this is something that I actually want you to just ponder for a minute and just like chew on this, mull this over in your head for a minute. How could we possibly multiply two vectors? What does that even mean, to multiply two vectors? Hmm. Hmm. It's an interesting question because if you think back to what we talked about in 12.2, we saw how to add and subtract vectors, and we saw how to scale vectors by a scalar, like a real number, right? Stretch it, shrink it. We know how to do that, but does it make sense to take two arrows and like multiply them in some way? What does that even mean? So, is there a mathematically consistent and relevantly motivated way to multiply two vectors? So the answer to this is yes. There's actually more than one way to do this. And one of the ways we're going to talk about right now, which is called the dot product. So here is the definition. This is what the dot product is. If we have two vectors A and B, then the dot product or the scalar product or the inner product is the scalar defined in this way. So what's happening here is we're taking our two vectors and we're multiplying the corresponding or the respective components, and then we're adding up those results. So we're doing A1 times B1 plus A2 times B2 plus A3 times B3. And the result is a scalar that we call the dot product, or more generally, a scalar product, because you get a scalar, or more generally, an inner product, because you can generalize this to much more interesting vector spaces. Okay, and just spaces. So one thing I want to point out, and I want you to note well, is that the dot product is a scalar. So when you perform this operation, the result is a scalar. For example, a real number or a complex number. The result is not a vector. So notice that when we added two vectors, we got a vector back out, right? When we subtracted two vectors, we got a vector back out. When we scaled a vector, we got a vector back out. Here, that's not what's happening. We are taking two vectors, we are operating on them in this way, and the result is a scalar number, a real number. So the dot product takes two vectors as input, and it outputs a number related to those vectors. It outputs this number, right? We'll talk about the intuition for this result in a few minutes here and like what that actually means. But this is algebraically what's happening. You're just multiplying the corresponding components and adding the results. That's the actual process of the operation, the function. Here are some very simple examples. If this is a vector A and this is a vector B, their dot product is just -1 times 6 plus 7 times 2 plus 4 times -1/2. Add all that up and you get 6. So when you dot these two vectors, the number you get is a 6. That's it. All right. um, Yeah, here we go. Oh, I didn't mention this before, but again, the dot product can actually be performed on vectors in any vector space. So we're talking about Vn. So the vectors don't have to be three-dimensional or two-dimensional or four or five or six or seven or anything. They can be any dimensional, and you can still define this dot product in a consistent way that makes sense. So here are some properties of this particular operator. If you've got vectors a, b, and c, and they're n-dimensional vectors, doesn't matter what dimension, then if you dot a vector by itself, you actually get the square of its length. So this is a helpful result. A dot A gives you the length of A squared. Yeah, and this one we're going to prove in just a minute here. One of the nice things about this operator, it's commutative. So A dot B is the same as B dot A. You can do that in either order, and everything's great. Commutativity of the dot product. Kind of like we saw previously, we have a distributive property. So if you want to dot A with a sum of vectors, then the A distributes dotly to each of those vectors B and C. You also have associativity of scalar multiplication here. And, or I should say, you can you can perform the scalar multiplication at any point in this process. So if you do C times A and then you dot that with B, that's the same as dotting A and B first and then scaling by C. Or you could scale B and then dot it with A, and you still get the same thing. So it's kind of like a associativity, commutativity of scalar multiplication here. And here's an important one. If you dot a vector with the zero vector, you get zero, the number zero. Remember, that's a scalar. So you dot two vectors, you get a scalar out. You get a number, not a vector. All right, so we're going to prove a couple of these properties. I leave the rest for you to prove on your own, and we're going to prove them in V3 just to make things a little bit clearer, but you could prove these in generality. So the first one is really interesting. When you dot a vector by itself, you get the length of the vector squared. And here's why it works. It's very straightforward, very clean result. A dot A, by definition, is A1 times A1 plus A2 times A2 plus A3 times A3, right? But this number here is just the square root of itself, I'm sorry, the square root of that squared. But remember that the square root of that sum is the length of A by the distance formula, or by that formula from the previous section, right? So long story short, if you dot a vector by itself, you get the length squared. Pretty cool. Commutativity is very easy to show. It really just follows from commutativity of real numbers. So A dot B, by definition, is this. But because these are all scalars, they're all real numbers in this case, you can use commutativity of multiplication for real numbers. So A1 times B1 is the same as B1 times A1, A2 times B2 is B2 times A2, A3 times B3 is B3 times A3. But now, by the definition of the dot product, this is equal to B dot A. So this is where the commutativity of the dot product comes from. And then lastly, A dot 0, well, the zero vector is just the vector 0, 0, 0, 0, 0, 0, 0 if you have n dimensions. So when we do the dot product, we get A1 times 0, which is 0, A2 times 0, which is 0, A3 times 0, which is 0. Add up a bunch of zeros, you get 0. That's it. Another thing I'll say, kind of a typographical note. Notice here that the dot product is a little bit bolder. So this is just a standard multiplication dot. The dot product, we use a little bit of a bolder dot just to indicate that it's that we're dotting two vectors, not two scalars. Okay, so that is the way the dot product works algebraically and some properties of it. Now let's try to build up some geometric interpretation, like some intuition for what's actually happening here. Because we've got two vectors, and remember, vectors are geometric objects, right? They're arrows. So the question is, if I'm taking these and I'm dotting them, what does that represent geometrically in my space? That's the question. And it turns out that it gives us a lot of important information. So in particular, it gives us a lot of information about the angle between the two vectors. angle between the two vectors. So before we can talk about that, what does that even mean? How do you define the angle between two vectors? So here's how we do it. The angle theta between two vectors A and B is the angle between the representations of A and B that start at the origin, and we require that the angle be in the interval 0 to pi. So in essence, imagine your two vectors are in their position vector position, right? And we just want to know the angle between them. Oops, like so. What is the angle between them when you put the tails at the origin? So literally, like, what's the angle between my two fingers right now? We require that the angle be between 0 and pi for a couple of reasons, but mainly it's because it makes this angle unique. We don't want to have two possibilities for this result. So we specify that the angle has to be between 0 to pi. All right, now we have what the angle between two vectors are. How does this relate to the dot product? And it relates to the dot product in this really intriguing way. Here it is. If theta is the angle between those two vectors A and B, then it turns out that the dot product of A and B is equal to the lengths multiplied and then scaled by cosine of the angle between them. So just stare at this for a moment and just ponder it, like mull it over in your head, look at the formula for a minute, and we're going to make sense of it in a couple minutes here. Yeah, length of A times length of B times cosine of the angle between them. All right, this one definitely needs a proof. And the proof is actually not so bad. We just use the law of cosines and then some of those properties of the dot product that we just talked about. So if we use the figure from before, in fact, let me go show you the figure one more time. This figure right here, right? So if we look at this vector B, this vector A, and this angle between them, that's what we're talking about here. So the law of cosines gives us that the length of the vector AB squared is equal to the length of OA squared plus the length of OB squared minus 2OA OB cosine theta. There it is. So literally just the law of cosines, right? Remember it back in the day, it was a C squared equals A squared plus B squared minus 2AB cosine theta. Same thing. Same thing here. All right, now let's convert everything into different notation. So the displacement vector between A and B is this difference right here. O and A is literally 0 minus A, OB, 0 minus B, and so on. So that's what this setup is right here. This vector difference just becomes A, right? Because the 0 vector is the 0 vector. So this just becomes A, this just becomes B, and so on. Now here, this is actually using one of those properties of the dot product. Remember that if you dot a vector by itself, that's the same as the length squared. So this is one of the properties of the dot product. So going from here to here is using that property. Now what we're going to do is we're going to use the distributive property of the dot product. So we're going to distribute this to each one of those terms, and then we'll distribute the result to each one of the resulting terms. In other words, we're going to FOIL. So this is kind of nice. This is kind of nice because foiling works the same way that it did for real numbers. So we get A dot A minus A dot B minus B dot A plus B dot B. There we go. Remember that the dot product is commutative. So A dot B is the same as B dot A. We're going to use that right now and combine these like terms. So if A dot B is equal to B dot A, then we've got two of these. So we have negative 2 A dot B. All right, now take a look at what we got so far. We've got length of A squared and length of A squared, gone. We've got length of B squared and length of B squared, gone. What's left? What's left is this term and this term, or I should say, there's this term, and that's what we get down here. All right, but look, we can cancel these negative 2's as well, and then voila, we get the result. A dot B equals length of A times length of B times cosine theta, which is what we were trying to prove. So that is what the dot product is. And this is going to give us our our geometric interpretation. All right. Now, as a corollary to this theorem, we get this important result. We can write cosine of the angle between those two vectors, a and b, as a dot b divided by the product of the lengths. That's it. That's it. So let's try this example. And this is one that I want you to try on your own using the dot product and using this formula that we just derived. Find the dot product of A and B if you know the length of A, the length of B, and the angle between them is 2 pi over 3. So first, think about how you're going to do that. Then say something out loud to yourself or to your dog or your cat, your sister, your brother, your axolotls, anything, or just yourself. All right, and now try to compute it using the formulas above. Okay, let's do it together. Pretty straightforward. We know the lengths and we know the angle, so we just fill in the blanks. Um, by the formula above, we have this. Length of A is 3, length of B is 6. Cosine of 2 pi over 3 is negative 1/2. Multiply all that together and you get negative 9. So A dot B is equal to negative 9. All right, now here's another one that I want you to try as well. So I want you to try to find the angle between these two vectors, 2, 2, negative 1, and 5, negative 3, 2. So try to find the angle between those two vectors. I think for this one, I'll jump straight to the thinker and the writer. Think about how you would do it and then try to execute it yourself. Okay, here we go. So if we're trying to find the angle between the two vectors, we can use that formula that said that the cosine, oops, was the dot divided by the product of the lengths. There we go. Okay, not so bad. So we just need to find the dot product, we need to find their lengths, and that should lead us along the way. Here we go. So first, the lengths. Using the length formula, we get that the length of A is 3, and the length of B is square root of 38. Then we can compute their dot, and we get that it's 2, so A dot B is equal to 2. And then the formula from that corollary, now we're just plugging in the results. Cosine theta equals 2 over 3 times square root of 38. And here's where we're going to use arc cosine or inverse cosine. So now what you can do is you can take the inverse cosine and you get that theta is equal to arc cosine of 2 over 3 root 38. This is about 1.46 radians or about 84 degrees. This is a good point to point out that this is one of the reasons why we required that the restriction that we restricted the angle theta to be in the interval 0 to 2 pi. This is what makes cosine inverse well defined. So if you remember from trigonometry or calculus 2, in order to define the inverse trig functions, you have to restrict the domain. And this is the conventional domain restriction for cosine. And the reason we do that is because that way when you actually do inverse cosine, you get a well-defined function. So that's another reason why we have that restriction. All right. Okay, so we've done a bunch of algebra. We have a very rough geometric interpretation of how the angle between two vectors is related to the dot product, but there's not a lot of intuition yet. Like, what is this dot product? What is it telling us? Like, how can we walk away being like, oh yeah, okay, the dot product is something that I could be comfortable with. So here's the big idea. The dot product is basically a measure of how aligned two vectors are. So what does this mean? This thing is kind of telling you how aligned two vectors are. And it's based on that angle, right? So imagine for a minute that instead of working with two non-unit vectors, you were working with two unit vectors. So suppose we had u1 and u2. Well, because their length is 1, this formula just reduces down to cosine theta. So what this means is that u1 dot u2 is equal to cosine theta. So in essence, what the dot product is doing is it's taking the lengths of the two vectors and scaling the result by the cosine of the angle between them, which is always some value in between -1 and 1. All right, so I want you to ponder that for just a minute. Ponder what I just said. Ponder these first couple of lines. Okay, so like read that a couple of times and let that sit in your head for a minute. Really, the dot product is helping us figure out how aligned two vectors are. All right, now furthermore, if two vectors point in the same direction, so imagine, instead of my fingers being like, oh, it's hard to see, there you go, like, like this, if they were literally pointing in the same direction, then what that means is that the angle between them is 0. So if the angle between them is 0, cosine of 0 is 1. So what that means is that their dot product is going to be the largest when they're pointing in the same direction. Literally, if the vectors are pointing the same direction, this number that you get is going to be as big as it could possibly be. That's what it's telling you. And if they start to deviate from each other, then what happens is this value of cosine changes. And so that shrinks the value a little bit because you're kind of like, you're multiplying that big number by something less than 1 in size. So you're shrinking the result, right? And it'll shrink even more until the two vectors are perpendicular. So this is another really important result. If two vectors are perpendicular, their dot product is 0. So if this vector is like this, and this vector is, it's hard to do, and this vector is like this, their dot product is 0. They're not pointing in the direction of each other at all. They are pointing totally orthogonally to each other. That's why you get a 0 dot product. All right? So ponder that again for a second. Just let that marinate in your brain, what the dot product is doing. Maximized when they're both pointing the same direction, starts to go to 0 when they pull apart, and they're at 0 when they're 90 degrees. What do you think happens when they keep tipping? What happens is probably what a lot of you are expecting. If the dot product is positive, then the two vectors have to be pointing somewhat in the same direction. So if you dot the two vectors, you get a positive number. You know for a fact the vectors have to be somewhat pointing in the same direction, kind of like, like this or something, right? If the dot product is 0, then the two vectors must be orthogonal. We're going to define that in just a moment. So you get a 90-degree angle when the dot product is 0. Then if the dot product is negative, that means the two vectors are pointing kind of away from each other. So it means, like I was doing a second ago, if they were like 90 degrees, oh my gosh, if they're 90 degrees, you get 0. And if they keep tipping away from each other, then what happens is the dot product is negative because it's basically kind of saying that one vector is pulling the opposite direction on the other in some sense. That's the idea. Positive dot product, roughly the same direction up to 90 degrees. If they're 90 degrees, dot product is 0. If the dot product is negative, they're kind of pointing opposite of each other. To some degree. How much of a degree? That's determined entirely by the angle between them and the cosine of that angle. That's the big idea. Okay, so this is one of the beauties of the dot product, is that the dot product allows us to define and formalize a notion of orthogonality, or in other words, perpendicularity. So how do you really define what it means for two things to be perpendicular? And how do you generalize that to 3 dimensions or 4 dimensions or 5 dimensions or 6 dimensions, right? It's not so hard when you're working in 2 dimensions. Okay, those are perpendicular, easy, right? Kind of like sends you back into grade school and you're like, oh yeah, I got it easy. Perpendicular. Even in 3 dimensions, it's not so hard, right? Ah, that's perpendicular, that's perpendicular, that's perpendicular. Every one of those axes is perpendicular to the other 2, right? That's not so hard. Okay, how do you extend that to 4 dimensions, or 5, or 6, or any number of dimensions? This is where the dot product comes in handy, because the dot product lets you define orthogonality. So, what does orthogonal mean? two vectors A and B are orthogonal if and only if the angle between them is pi over 2. So perpendicularity and orthogonality are basically the same thing. A little note at the bottom here. Oops. Little note at the bottom here. The zero vector is considered perpendicular to all vectors, just because it's the zero vector. It's special, right? So we get this theorem here, which is actually an equivalent definition of orthogonality. So we defined orthogonality as the angle being pi over 2 or 90 degrees, but you could equivalently define it as having a zero dot product. That's what's so handy about the dot product, right? The proof is very straightforward. Two vectors are orthogonal if and only if their dot product is 0. Well, if they are orthogonal, then the angle between them is pi over 2. And so that means this cosine of pi over 2 is equal to 0. So their dot product is equal to 0, right? So that was, if orthogonal, then dot product is 0. Now let's go the other way. So if the dot product is 0, then they are orthogonal. So if the dot product is 0, that means that this equation has to be equal to 0. And assuming these are not the zero vector, if they're the zero vector, we're already done. So assuming these are not the zero vector, cosine of 0 would have to be 0. That's the only possibility if these are not the zero vector. But if cosine of theta is equal to 0, then the angle between them has to be pi over 2, that unique angle in the interval 0 to pi. And that means they're orthogonal by definition. So you can take this as a definition of orthogonality. That's what I'm trying to get at. Orthogonality means the dot product is 0. The dot product is 0 means the two vectors are orthogonal. That's the big idea. Okay, so let's say you come across a question like this. Show that the two vectors here and here are orthogonal. You try this one on your own. I'm just going to jump straight to the writer because I'm pretty sure you could do it pretty quickly. Show that those two vectors are orthogonal. All right, so all you got to do is take the dot product. When you dot these two vectors, you do the algebra, you do the arithmetic, and you get 0. That means that they have to be orthogonal. So these two vectors are literally at a 90-degree angle to each other in three-dimensional space. There you go. All right. All right, so now that we have this notion of orthogonality and there's this relationship to angles in between vectors, we can talk about what are called direction angles. Yeah, so this is giving us a way of talking about these angles. There are some common angles of interest, and in particular, these are what are called the direction angles. So yeah, I shouldn't say point. um, a common question of interest is what angle does a vector make with the coordinate axes? So for example, if I've got this vector A, what angle does it make with the x-axis or the y-axis or the z-axis? What is that angle? Well, those angles are called the direction angles of the vector, non-zero vector. We denote them by alpha, beta, gamma, basically the Greek ABC. Like before, they have to be in the interval 0 to 2 pi so we can maintain uniqueness. And that's just all they are. So the direction angles are the angles a vector forms with the axes. Using the corollary above, or honestly at this point, just right triangle trigonometry, uh, then you can figure out what this angle is. You just you take your vector A and consider the basis vectors I, j, k. Use the formula we just derived, and you get what are called the direction cosines. So the direction cosines of a non-zero vector are these values. Cosine of alpha is this. Cosine of beta is this. Cosine of gamma is this. And that's it. This is another one of those moments where what I want you to do is look at this figure and look at these formulas and then try to see if you can use right triangle trigonometry to see where these formulas are coming from. So just ponder it for a minute. Maybe I'll give you a little hint. Think about that. Okay. Um, yeah, so the reason that I wanted to write this on here is because if you're thinking about right triangle trigonometry and maybe even remembering that physics application from the previous section, what this is saying is that the x component is basically the length of A scaled by cosine of theta. Oh, I'm sorry, not theta, my bad. Let me fix that. That should say alpha. My apologies. There you go. Right? So you take the length of the vector A, you multiply it by cosine alpha, and what you get is you get the x component, right? You get the x component, which makes sense. Similarly for uh, cosine beta and cosine gamma. So one of the cool things about direction cosines is they give you a lot of cute and convenient results, just so many cute results. Here's one of the ones that I just pointed out. And again, this really just follows from right triangle trigonometry. There it is. So the x component is length of A times cosine of the angle that the vector makes with the x-axis. The y component is the length of A times the cosine of the angle the vector makes with the y-axis. The z component is the length of A times cosine of the angle that it forms with the z-axis, right? Makes sense. From this, maybe you can try this one on your own if you want to just have some fun with it. From this, you can actually get this result. Cosine squared alpha plus cosine squared beta plus cosine squared gamma equals 1. It's a fun little algebraic calculation, so if you want to do it, go for it. Um, we also get these two results. Again, lots of cute results from direction cosines. We have a new way of writing any arbitrary vector, any arbitrary vector. Let's say we have a vector A given by A1, A2, A3. Well, from the corollary just a moment ago, we can rewrite each one of those components like this. Oops, sorry, that's a typo. This should say gamma. Oops, there we go. Right? But again, just by the definition of scalar multiplication for a vector, we can factor out all of these factors of A and pull it to the front, or length of A and pull it to the front. And then you just get that this vector A is the same as its length times this vector, which consists of cosine alpha, cosine beta, cosine gamma, which is pretty cute. It's pretty cute. What's even cuter is that if you want a unit vector in the direction of A, you just divide that by the length of A. But when you divide it by the length of A, it cancels this factor here, and you're just left with cosine alpha, cosine beta, cosine gamma. So one of the cool things about this is if you want to know a unit vector in the direction of some vector A, it's really just cosine of alpha, cosine of beta, cosine of gamma, where these are the direction angles. Oops, there you go. Cute. Very cute results. Okay. All right, so now moving along with angles and this notion of angles between things, this lets us talk about vector projections and then scalar projections. This is one of the moments or one of the times where you really want to try to use some intuition because the formulas are going to start to get complicated. You don't really need to memorize most of these formulas. I'll tell you the stuff that you need to memorize for an exam, but really you want to try to build intuition for these ideas because when you get lost in the thickness of the formulas, intuition is going to help you find your way. So this is a good example. Here, what is a vector projection? So the vector projection of B onto A is denoted by proj sub A of B, and it's basically the shadow vector that B casts on A. So intuitively, that's what it is. Let's take a look at the figure here. We've got this vector here, the vector A, and this is the vector B. And the vector projection of B onto A is basically the shadow that B casts on the vector A, right? Does that make sense? I think that makes sense. It's the shadow that you get when you basically, if you were to put a light, if you were to put like a spotlight here shining down, then this vector here is the shadow that B casts on A, and we call that the vector projection of B onto A. right? So here's one image of it, or one example of it. Here's another example of it, right? It's not that B even needs to be like hovering over A. It's defined as the shadow that it would cast on A. So here A and B are actually pointing in opposite directions, or like they're not pointing in the same direction at all. And the shadow that B casts is this vector. So that's what the vector projection is, literally the shadow vector. Um, Little note, notice again that the vector projection is a vector. So the result of this function that you get by putting b into it is a vector. So it outputs a vector. Now compare this to the scalar projection. Luckily, the scalar projection is also very simple. The scalar projection of b onto A, also called the component of b along A, is just the magnitude of the vector projection, except it could be positive or negative. That's it. So vector projection is the shadow vector. Scalar projection is the length of that shadow vector plus or minus depending on the relationship between the two vectors. That's really all it is, right? The scalar projection or component of B along A that's denoted by comp sub A of B. And again, frankly, by right triangle trigonometry, you get this, that the formula for the component of B along A, wait, sorry, did I say that? But yeah, component of B along A, it's length of B times cosine theta. That's it. And again, it's really just right triangle trigonometry again, right? Think about this is the length of B right here. What's the length of this? It's this times cosine theta. So trigonometry, once again, comes in so many ways. And that's what we define as the scalar projection of B onto A. Now, maybe conversely, or not conversely, but similarly, the scalar projection is a scalar. So when you do the scalar projection, you are getting a number. You're getting a real number in this case, or complex number. You're getting a real number. This is not a vector. So the scalar projection is a scalar. The vector projection is a vector. The scalar projection is literally just the length of the vector projection plus or minus, depending on the relationship, right? Okay. So now that we have this intuition for what the vector projection and the scalar projection are, we would like to have some formulas that relate it to, say, the dot product. Remember, the dot product is the one that kind of connects everything to the angle between these two vectors. So recall this formula, that the dot product is length of A times length of B times cosine theta. But if you look closely, this piece is literally the scalar projection of B onto A. The scalar projection of B onto A. So here I kind of emphasized it, right? I pull that off, and this is the scalar projection of B onto A. That's what it is. It's the component of B along A, right? So one of the ways you can interpret the dot product intuitively is it's the length of the vector times the scalar projection. So yeah, this is where I say it right here. So in some sense, you can think of the dot product as telling us how much of an effect B has on A. It's like how much B is pulling on A in some sense, right? But again, because the dot product is commutative, you can also think of it as how much A is pulling on B. So you have this kind of like connective relationship, which is pretty cool. Um, all right, all right. So now that we have these formulas, you might have noticed if you look back through the slides that we didn't actually have a formula for the vector projection, right? But wait, do we have a formula for the scalar projection? We do, yeah. We have a formula for the scalar projection. What's a formula for the vector projection? Well, this is how we're going to get that. We know that A dot B is length of A times, oh wait, hold on. Good, good. Yeah, I don't have a typo. Whew, that's good. um, yes, okay. So another way of interpreting the scalar projection is this. You can think of it as a unit vector in the direction of A dotted with B. So that's the scalar projection. You got like the direction of A dot B, and that gives you the component of B on A, along A. That's pretty much it. So how do you get the vector projection? How do you get the vector projection? You take a unit vector in the direction of A and you multiply it by the component of B along A, the scalar projection. This is why I was saying the intuition can help guide you through the thicket here, because this is basically the formula. The book uses a slightly different version of this formula, but it is equivalent. It is equivalent. The reason that I like to use this particular formula, or at least the structure of the formula for the vector projection, is because it's basically saying uh, to find a vector, a unit vector in the direction of A, and multiply it by this, the scalar projection. That's it. And that's pretty much it. Um, yeah, that's it. So we'll practice this in activity. You'll practice it on homework. But if you ever get lost, just go back to these images here. Think about what's the vector projection and think about what the scalar projection is. And that's how you can relate the two. Okay. Here we go. So this one I want you to try. You can reference those formulas, but find the scalar projection and the vector projection of this vector B onto the vector A right there. So think about it for a minute and how you're going to start it. All right. And now say something out loud to yourself about how you could start it. Just give your brain that verbal feedback, something out loud to let your brain hear what you're thinking. All right. And now try to work it out. You can look back at those formulas. That's okay. You don't need to have them memorized, but try to identify the pieces of them. All right, here we go. So scalar projection, well, one of the things is we're going to need to know the length, right? We need to know the length. We have some formulas. We need a unit vector in the direction of A, so we need to know the length of A. Length of A is going to be square root of 14. We can use those formulas from corollary 6, and we get this. We're going to do unit vector in the direction of A and dot it with B, which gives us this. So this is the scalar projection of B onto A. This is like the effect that B has on A in terms of like length. Now, what is the vector projection? We're just going to take a unit vector in the direction of A and multiply it by this number. That's it. So this is one of the reasons why I prefer the format that I have here as opposed to the one in the book, because it's very easy to see what you're doing. You compute the scalar projection, and then from that, you just multiply that by a unit vector in the direction of A, and you got the vector projection, right? And again, remember, it's easy to get lost with, am I working with a scalar or am I working with a vector? It's really hard, it's easy to mix them up. Well, you're going to see some questions on the homework that will help you work on that. But again, this is a scalar. So we have a number. This is the scalar projection. If I want to know the vector projection, well, I've already got the size. I've already got the size figured out. What I need now is the direction. That's why we do this. We take the size that the scalar projection gives us, and we multiply it by a unit vector. And that's all we need to do. And that gives us the vector projection. So we got a vector here instead of a scalar, right? Okay. All right, so now last bit here is a physics application, work. We're actually going to see work again in some very important ways later on. I think it starts in chapter 16 actually, but I feel like if I remember right, we look at it a couple more times. So projections are used a lot in physics to calculate work and how much work is done. So the work done by a constant force F in moving an object through a distance d is given by this formula, work equals force times distance, which makes sense, right? You move something, you have to apply a certain amount of force along a certain distance. That's how much work it takes. All right. The only catch is that this formula is only valid when the force is directed along the line of motion. So this is why if you look at your old textbooks and from like Calc 1 and pre-calc, these types of questions, everything is moving in a horizontal line, right? Well, we're going to generalize that in this class, and we're going to go up into situations where the force is not being applied in a straight line, like along the x-axis, right? But this formula only works when the force is directed along the line of motion. So let's say the line of motion is given by the vector PQ. Here we go. Here's the vector PQ. Here's the force that's acting right now, and the length of PQ is I'm sorry. This is the vector PQ, which we're calling D, because this is giving us the displacement vector. So suppose we got a constant force given by this vector F, pointing in some arbitrary direction. Then we're going to say the displacement vector is the vector PQ. We'll call it D. And we want to know the work done by this force in moving the object along this vector. So what is the work done? Well, the work is the product of the component of the force along D and the distance traveled. Okay, that's a mouthful. That's a mouthful. So the work done is the component of the force along D times the distance traveled. There we go. That makes more sense, right? It's that how much of the force is going in that direction, and then how far you applied the force, like how much time you can say. So in other words, work, by right triangle trigonometry again, work is the component of the force along D times the distance traveled. The distance is the length of the vector. So we get that work is length of F cosine theta times length of D. Do some massage, move pieces around a little bit, and we get length of F times length of D times cosine theta. That looks really, really familiar. That's right, it's the dot product. It's the dot product. So the work done is the dot product of those two vectors. Ah, pretty cool. Pretty cool. All right, now let's apply. Here we go. Classic example, there's a wagon that's pulled a distance of 100 meters along a horizontal path by a constant force of 70 newtons in the direction of F, right? Here's the force F right there. So you're pulling a wagon. Just imagine you're pulling a wagon, right? That's the idea. The handle of the wagon is held at 35 degrees above the horizontal path of motion. How much work is done by the force? That's the question. All right, I'm going to throw the thinker up on the screen for a minute, ponder this for a minute, think about how you would approach it. Right, now say something out loud to yourself about what you want to use to start. Anything out loud at all. And now, see if you can calculate it. Try to work it out on your own, and we'll do it together in just a moment. All right, here we go. So we're going to use this figure here, and we're just going to use the dot product, frankly. So the computation is really quite straightforward. Work is F dot D. We have a formula. We know the length of F. We know, sorry, wait, hold on. Hold on. Oh, yeah, constant force of 70 newtons. Yeah, so the size of F is 70, the size of D is 100, and we have cosine of 35 because that's the angle between these two vectors. Then go to a calculator, we get an approximation of 5,734 Newton meters or 5,734 joules. And that's the idea. You know, I had said this was the last bit, that there is one last little bit at the end, which is helpful technology, which is Mathematica. I've kind of said this a couple times already. It's incredibly powerful. It's got a lot of built-in functions that can make our life easier, more efficient. We're going to use it throughout the course. In this section, a helpful command is simply dot. And by dot, I mean a period. And Mathematica treats the dot as a dot product. It gives the product of vectors, matrices, and tensors. We're not going to worry about tensors in this class. So in our case, it'll compute the dot product of any pair of n-dimensional vectors. Another thing I forgot to mention earlier, the dot product works in any number of dimensions. So all those formulas that we saw already, that all holds no matter how many dimensions you're working in. Could be dimension 1 billion, and it'll still work. So I'm going to do a very, very quick example with Mathematica of using the dot command, and we're going to dot these two vectors here. Let me pull it up. Where are you? There we go. Okay, there we go. Got it. All right, so let's dot these two vectors, and here's how we're going to enter it. We're just going to enter it using curly braces. So our first vector was 1, 2, 3, 4, 5. Oops. There we go. 1, 2, 3, 4, 5. Mathematica takes a vector as a list, so you use the curly braces. And then we're going to do a period, that's the dot. And then -4, comma, 8, comma, -1.3, comma, 7, comma, 6. And then shift return gives us the dot product. You can also use the command dot. So you could actually do dot, see, and it'll give you a list of, oh, you can't see the pop-up. Interesting. It'll pop up with a list of possible commands that you were trying to type. In this case, dot is what we want. And we're just going to put these two vectors in there. I'm going to copy paste dot this, comma this, shift return. Ooh, oh, forgot to close it. So it'll give you an error sometimes, like it'll throw an error. Here it says this expression has no closing bracket. Nice, thank you. So let me include the closing bracket. It actually kind of lets you know that there's an error here. It's like, hey, red bracket, you're missing a piece. There we go. Oh, let me zoom in. Sorry, I realized this is kind of small. Maybe a little bigger even. There we go. Sorry, I know it's kind of hard to see. There we go. So now we can close this. Boom, there we go again. Nice. So Mathematica can do the dot product for you. Okay, now let's go back to the slides. There we go. And then last little bit, do you think this just confirms what we did? Yep, that's it right there. All right, and then on that note, let's play. So I'm excited to work with you all on this in activity, talking about the dot product. The next section is actually on what's called the cross product, and we'll do that in the next activity after that. So I'll stop rambling. This is already getting a bit long. Thank you again for listening, and I'll see you all next time.